Hello and welcome to another video. In this one, we're going to be talking about how I debugged and then fixed PyuWSGI in Python 3.12. In the previous video, I talked about how I became a maintainer and walked through some of the debugging of what I thought was fixing the problem, but it turns out that I didn't. I'm going to do a quick recap of that, and then we'll dive into my debugging process, how I figured out a bunch of stuff about how uWSGI and PyuWSGI work, as well as even stuff related to subinterpreters. But anyway, let's jump into it. I guess the subinterpreters part is a little bit spoilers. We're not actually going to be involved with subinterpreters, but some of the work was related there. Anyway, in order to set the stage, I'll describe to you the original issue that I started with was hoping that a previous release or a future release of uWSGI was going to fix the problems that I was seeing. The problems that I was seeing was running uWSGI with this particular set of settings. Yes, there's a lot of settings here. I ended up minimizing this down later, but we'll get to that. With a simple uWSGI app with threads enabled and a very basic hello world program would result in a deadlock after it reloaded, after it reached a certain number of requests that the worker was done and needed to start over. And I ended up taking on maintainership in PyuWSGI, one of the ways that uWSGI is packaged, and upgraded it to the latest version. Blah blah blah. Got added there. Ended up getting a release. Hooray! And then I ended up with a bit of problem in that after trying out the newest release, it didn't fix my problem. And so what I did is took the problem, that original large set of settings, minimal app, minimal execution, and tried to narrow it down to the smallest possible reproduction. Basically taking just pip install PyuWSGI, again, a simple uWSGI app. I've changed it a little bit from the other time just so that it's easier to see the output, just one dot at a time and one exclamation mark at a time. That way you can see it doesn't spam the console as much. And a much smaller set of settings. Now, some of these aren't necessary for reproducing the problem, but we're to make it a little bit easier to see the output. So for instance, like somewhere in here, I have disable logging. Yeah, disable logging so it doesn't spew output, and max requests of 5 so it restarts sooner. But the same sort of curl command, and I'm actually going to show you this particular reproduction just so that we can start from somewhere at the same time and start to understand the problem. All right, so we're gonna bash. Editor, right. So we're going to set up a small shell script with the same contents. We're going to make a virtual env in the same way as before. And in Python 3.12, to reproduce the problem, we're going to activate that virtual env, and we're going to pip install PyuWSGI. And I guess specifically to make this video future-proof, we're going to install 2.0.26. Spoilers, I have fixed this in 2.0.27 alpha 1. I basically cherry-picked a patch to fix it. We'll get to that patch eventually. Anyway, install PyuWSGI, set up this little wsgi.py file. WSGI, off by one on my keyboard there. Wsgi.py, and if we run this script here, we've spawned uWSGI, and if we go to another tab, it's a bad video when I have 4 tabs, because we're going to need all of them at one point throughout this. But anyway, we run this, and you'll see that we eventually get to a point where it respawns the workers, but you can see it's no longer processing requests. It is deadlocked here. So started with that, got a minimal reproduction. Great, awesome. This minimal reproduction ended up being extremely helpful throughout this process because I was able to basically see if I fixed it or not, depending on whether this worked or not. Blah, 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 and just showing the reproduction and eventually the unkillable state. I pinged one of the other people that had been contributing to uWSGI and seemingly in related spaces, dealing with reloads and threads. And this other person recommended some other things to try, ended up applying those patches. They didn't really fix the problem. Try the patch out, doesn't seem to fix it. And so then I kind of shifted gears and went into more of a debugging mind state. And so I wanted to figure out what the processes were doing. And so I used strace, which is a tool to look at the syscalls that are happening. So which strace, strace help. Basically, you can tell it a PID to attach to. P. Somewhere in here, but maybe it's just the PID directly. But basically, I could figure out which processes were running and what they were doing, or some of what they were doing. Grab uWSGI, and so we can see here we have 3 processes. One is the parent process, this 672, and these are the forked children processes. We can just take one of them and sudo strace. I have to use sudo because it needs to do kernel-y things that you usually wouldn't want user space to do. You can actually use strace to spawn the process, and then you don't need root, but we're going to use root here. And my bad password. Oh no, you typed a password with, oh, it's gotta be -p then. Typed a password with a keyboard cam. Yeah, the password is bad password. Okay, so if we strace one of the children here, you'll see that it's doing this same thing over and over and over. This utext call and then getting e timed out. I happen to have spent a lot of time using strace and figuring out some of the common syscalls, and I happen to know that futex is a call to take a lock. And so the child processes are continually trying to acquire a lock, and in particular, they're trying to acquire the lock with some amount of timeout. I think it's one of these parameters, not really sure. I don't think it's this one because 4990 seconds is a very, very long time. But basically it's trying to acquire a lock and then timing out and failing. So there's a spin lock happening somewhere. I also wanted to look at the parent processes. So if we look at this and we do sudo strace -p, this one, you'll see that the parent process, and this is actually kind of normal to what uWSGI does in general, it's waiting on some ID process group, I don't know. And also trying to retrieve things from a socket and just kind of spinning in a normal loop. This is pretty normal to what uWSGI does in general because it's trying to pick up requests from a socket queue and then hand them off to workers. So there wasn't really anything weird going on in the parent process, but that child process on that spin lock was a little bit weird. So I wanted to figure out even more in depth how I could figure out what this child process is doing. And so I reached for GDB. GDB is a debugger for, I guess, just programs in general, but in particular, it's useful for C-like programs. And similar to how I attach to the process to look at its syscalls, I can attach to the process and see what its execution is doing. So let's grab those processes again. And we're going to not really care about the parent process because it's not going to be that interesting here, but we're going to look at what the children are doing. And so we can do sudo gdb-p the child, and it's going to load a bunch of symbols and tell us that we are at epoll wait. We can ask w to tell, or where? Yeah. We can call where, and it'll tell us the list of function calls that we're at right now. And oh, it happened to pull in debug symbols. Interesting. Cool. That's helpful, I guess. But you can see we're at epoll wait inside this. Inside. Oh wait, this is the wrong process. Did I paste the parent process? This looks like. Yeah. Make sure I got the right process. 7.2. Oh yeah, I grabbed the wrong process. Okay, anyway, that's what the parent process looks like. It's very normal, the master work loop, which is what uWSGI calls it. So anyway, let's attach to a child process, since that's the interesting one that we care about. We can again say where, or bt is backtrace, which will tell us what's being run right now. And you'll see this futex abs timed wait common 64, anyway, kernel stuff. This is the acquisition of a lock in pthread condition timed wait 64 is, you know, this is the deepest thread, so the one that's running. Anything going down is higher and higher. In Python, you'll see stack trace is kind of in the opposite direction, where like the most relevant frame is at the very bottom. The idea from Python for that is that if you're running something in a terminal and something crashes, you look slightly up from where it crashed, and that's the most relevant stuff. Whereas in a lot of other languages, it's flipped the other way around. That's why when Python says, you know, most recent frame first or last, that helps you understand there. But anyway, we need to page down because this isn't really telling us much. This is all just C library kernel functions here. We do actually see PyCond timed wait. That's actually the first Python frame that I think we see here. And if we look further down, we see this pyeval restore thread, which is a C function, and we see uWSGI Python master fixup. And and this is the important function, take GIL. So it seems to me like the child processes are trying to take the GIL. If you're familiar with the GIL, or if you're not familiar with the GIL, I have a video on it, a couple videos on it. I will link those in the description. Basically, Python has a global lock for execution, and it looks like here it's trying to acquire the global lock and it's been looping for some reason. Potentially because something else is held or holding it, or some other weird behavior. We'll actually figure this out later in the video, so I don't want to completely spoil it yet, but this was kind of my first hint as to what was going wrong here, as well as some functions to kind of understand what execution is happening, so I can look at them later and figure out what's going on. Okay, cool. You'll also notice in my bug report that I had eliminated a few variables here, and so I wanted to dig into those next to try and figure out if I can learn more about why this bug is happening. In particular, I realized that this only happens in PyuWSGI. It doesn't happen in normal uWSGI. It only happens with threads enabled, not with threads disabled, although there's really no reason, and I can't think of a valid reason why you would run uWSGI without threads enabled. Threading has been part of Python since forever, and I think in Python 3 it was made required, or 3.4 or something like that. So I don't think that, disabling threads is actually something worth looking into. And I also noticed that Python 3.12 was the only thing that triggers this. Python 3.11 doesn't trigger this problem. And so this kind of told me, digging into this particular problem first, this kind of told me that I knew some case where it was working, and I knew some case where it wasn't working. And somewhere in between, it went from working to not working. And if I see a pattern like that, I reach into my toolbox for git bisect. I've actually done a couple of videos on bisect in the past, one on bisecting a bug in Node.js, and another that just sort of introduces bisect in general. And so I will link those in the description. But spoilers, I went to bisect CPython to figure out when did this behavior change. Maybe it's a bug in Python, maybe it's a bug in uWSGI. I didn't know, and I wanted to figure out more about the bug and hopefully lead me down the right direction towards solving this. So what I did from here, actually, let's quit out of GDB here, and this process is actually in a very stuck state, so we're going to background it with Control-Z, and then we're just going to kill -9 it. Actually, no, I have to foreground this so that the background process go away. This process doesn't respond to Control-C or even Control \, which is a quit. So there isn't really a good way to kill this. Or sigterm. Sigterm didn't kill it either. But anyway, very dead now. So the next thing that I went to do is bisect CPython. And actually, I basically took this shell script in this Python file and made a minimal reproduction that I could test on each version of Python. Well, it doesn't actually do each version at bisect, so we know our bounds. Let's try one in the middle. Okay, if it's good, then we know that we can eliminate all of these commits as the problem, and it must be these ones over here. Basically, log n to figure out where the regression was. We're actually going to cd into a directory because there's a lot of setup that I had to do for this. It should be in bisect uWSGI 3.12. Yes, okay. So a lot of stuff here, but I basically wanted to narrow down a better lower and upper bound. Mostly because the way CPython development works is they do different minor versions on different branches. And so bisect works a little less good if you have to go across the two branches because it has to find merge bases and all sorts of fiddly git stuff. But fortunately, very, very early on, CPython, minor version development usually starts with very few changes from the previous version. So basically what I did is I took that little shell script and manually tried to figure out two bounds here. And I found out that 3.12 alpha 2, which was, I think, the second tagged alpha release. I don't remember why I didn't use alpha 1, but 3.12 Alpha 2 was successful in that it had the same behavior as Python 3.11 and was able to reload successfully. And I noted that release candidate 1, which is usually when Python stops making major changes in its release cycle, was not working, was bad. I mean, I use good and bad here. It's not necessarily CPython's fault. We'll see later. But I had 2 bounds, and from that, I knew that I could try and figure out where in between those the behavior changed. And so what I did from that is wrote a Python script. I could have done another shell script, but I felt in my bones that this this bisection was going to be a lot more complicated, and I was going to have to do a lot more work to figure out whether it's good or bad. You know, as a human, it's really easy for me to run that shell script, then run a bunch of curl commands, and like sort of intuitively know when it reloads and like whether it's stuck or not. But doing that automatically is a different story, and so I needed something a little bit more powerful than just shell scripts to figure that out. So I made this bisect uWSGI script, and we'll actually start at the bottom since I think it reads. I tend to write scripts from bottom up, and so we'll read it that way. And basically what it had to do as part of bisecting is build the current version of CPython that I'm on, make a virtual env from that version of CPython, install uWSGI inside of it, and then run the test that we had figured out from before. Basically something similar to that shell script and something similar to the requests workload that we ran before. And I guess we'll go over each of these functions. They're not that, the first 3 aren't that interesting. Build CPython, basically clean out any previous state, run configure against a prefix, install it to a particular location, run make with some subprocesses. On my old computer, I only had 5 processes for my VM, so I chose 5 here. I could have done j0 or whatever, and then install it into this prefix. Next from that, I made a virtual env, basically delete the previous virtual env, and then run the venv module to build a new one. Then install uWSGI into it. I had a clone of PyuWSGI local to this so that I could install the same set of source each time. And then finally we have our test, which needs a little bit of explaining here. Our test is kind of set up in a couple of ways. First, we start uWSGI with this context manager, and basically that is just set some environment variables, basically the same as that shell script. I used log files so that later I could look at this and figure out what happened and not spew to standard out. Start the process itself, wait until it's up. Wait for ready is basically just try and request the port that I chose until it responds with a 200, and then yield that PID. You'll notice here that the finally is a little bit complicated. I needed to figure out all of the processes that were running and then kill them. This is basically that pkill-9 uWSGI that I had before, but in this case I'm using psutil, a third-party library to figure out the process tree of PIDs in order to kill them. And I did this because I didn't want any state from a previous run to be left over in the future. And I didn't just use pkill-9 with -f, which finds anywhere in the process for the word uWSGI, and I found that I kept killing my editor because this uWSGI.py was in the command line string, and so I was nuking myself. And so this is very specifically just the process tree that we spawned to make it very specific here. I'll show these bits up here since they're short little helper functions, but helps understand this. Rec just makes a simple request with a timeout. We later use this timeout to figure out whether it's successful or not. This wait for ready is just kind of a spin loop, and I probably a later version of this has an else here that I should have put here, but like else raise assertion error never ready. But I was doing this on the fly and just hacking stuff together and doing whatever needed to work. And then later and also there's this child PIDs, which uses psutil's children to figure out all of the children PIDs. All right, so all that context, we start uWSGI, we know its set of children, and then we basically just run a loop run a single request. If the request times out, we know that we've probably got to a deadlock. I check a little thing and make sure that we've actually recycled to new children, and we know this is our error case here. So we make requests until they time out. They should respond within a second because it's local and it's just a single byte being transferred, so it shouldn't be that big of a deal. And if it doesn't time out, we know that the request was successful, and we can check if the children are exactly the same. If the children are the same, we know that it hasn't forked off new children, and we don't know whether it's good or bad yet. We only know if it's successful if it has completely recycled all of the children and a successful request occurs. So that's basically what this does here. And yeah, then we know whether it's successful or not. So this is kind of our test as to whether something is good or bad. All right, given this script, I was able to run git bisect against this. The basics of git bisect are, just show you really quickly. I'm not going to actually run it because it took about 30 minutes to get to the actual finding of the commit. But you basically do git bisect start. This tells it that we're in bisect mode. Then you do git bisect bad with whatever revision. In this case, it was v3.12.0 alpha, or no, good. It doesn't matter if you do good or bad first, but anyway, I usually like to do good first because how I think. You can also use different verbs than good and bad. Like I think there's some coloring, like blue and red or something, blue and green. I don't know. But anyway, good, we know it's this version. And then you do bad v3.12.0 rc1, tell it the bad revision. And then you finally tell it what command to run. And in this case, it was, I think I had a virtualenv specifically for my bisection in Python 3, and then that bisect uWSGI script. So I kicked this off, did some other stuff. I actually did this on stream, and then waited for it to tell me what the bad commit was. And did I keep that note here? I did. Okay, so after running that bisect, scroll down, try lazy apps, didn't try that. And anyway, after running the bisect, git bisect spits out this little output here and tells us blah 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 is the first bad commit. Okay, so given all of that, I looked at this commit and scrolled through it, and I made some guesses about what was happening here. The commit message here actually I thought was very funny. Make sure the GIL is acquired at the right places, whatever that means. But I looked through this patch and I noticed one particular thing about it. Where is the thing? It is not here. But spoilers, yeah, this patch changed behavior and was the first one that caused this deadlock to start occurring. I guess spoilers, calling it a deadlock, but we'll get to that eventually. Okay, yeah. So here is kind of the core of the change in this pystate.c file. And I didn't really understand this at all, and still don't completely understand all of the thread state and GIL management that happens in Python. But at this point, I was just formulating some hypotheses, and something stuck out to me that looked different. In particular, this original version of PyThreadState swap is now this swap thread states, and there's no GIL management happening at all inside of the old version of this. Swap thread states is the new version. If we now look down here at PyThreadState swap no GIL, and saying that it doesn't do any GIL management here, it just calls swap thread states. And the new version of PyThreadState swap, as the old version was up here, is now doing some GIL management here. It's releasing the lock in the old thread state and acquiring the lock in the new thread state. And spoilers, this GIL management triggered this bug. Now, it isn't necessarily CPython's fault, and we'll actually show later why this is uWSGI's fault, or specifically PyuWSGI's fault. But I noticed this change here, and I thought, this function PyThreadState swap here just called this underscore version. And so prior to this change, there was no lock management happening here. But after this change, there suddenly was lock management. And so this is a externally visible behavior change in CPython based on this public API. which normally I would guess is, something that should be called out in the changelog. But we'll actually find out later that the behavior change here shouldn't have mattered because it was really only doing things that were within the defined behavior of this function. I should have opened the docs here and scrolled through those to show you this, but basically the docs tell you like you must have it held before and we'll have it held after or something like that. But so anyway, we identified a behavior change, and my initial thought was, well, let's just try and revert the behavior back to the old behavior and see if that fixes the problem. So I'm not going to show that here because it's actually a lot of work to recompile CPython. Well, not a lot of work. It's just going to take a while to do it. But I reverted this to the swap nogil function and made a patch to CPython with that particular change here. And when I built this, it worked. My little test succeeded and things were reloading successfully. And I got all excited. I was like, oh, yay, I can fix this and just restore the behavior back. This function actually doesn't exist in 3.13 due to the free threaded work, but that's unrelated. And so I was like, cool. I thought I fixed this. I thought I got to the end of this problem, but it turns out, no. This patch caused all sorts of test failures in CPython, and so this was not a good patch and not the fix to the problem. And actually, when I went back and looked at the output of uWSGI during this, the only reason it was successful was because CPython was segfaulting, and then uWSGI was bringing up a fresh version that happened to work. And so, yeah, it succeeded unsuccessfully. But this basically took me back to the drawing board, and I needed to figure out what was going on here. At this point, I sort of had a hunch that because changing back the behavior of PyThreadState swap was not fixing the problem, that maybe uWSGI was in sort of a weird undefined behavior or incorrect state, and it was actually uWSGI's fault and not Python's fault. And so from there, I tried to figure out what was going on, where the problem possibly was. And I did a whole bunch of debugging on CPython. I'm going to show you just some of that and some of the stuff that I figured out and like played around with to try and understand the problem. But basically, I just started adding prints to CPython and using a lot of GDB to step through. Debug PyuWSGI, and also adding some prints to PyuWSGI itself and figuring out things there. And one thing that I noticed while doing this, if we look into CPython and shows some of the diff of the things that I was trying, this ended up being a dead end. This is where it was segfaulting, but I wanted to figure out what was going on there. One thing that I found really weird and actually confused me a lot during my debug session is I added prints and I was often seeing them doubled in ways that should be impossible with like the wrong PID and like the wrong output, and it turns out that was all a red herring because I was missing an flush command. Now, my understanding of standard IO in C is that if you have a new line at the end of printf, you shouldn't need this flush. It should just be line buffered and print it normally. But then I remembered that uWSGI actually does some strange stuff to standard IO. And the reason that I remember this, and Python and uWSGI both do some strange things to standard IO and configure them in ways that are not necessarily what you would expect, mostly for performance reasons and micro benchmarks. But I actually knew this because I patched uWSGI back in 2016 to adjust this behavior for Python 3. And this was a very, very long time ago before I really understood open source. And yeah, I'm not, despite this patch fixing a problem, I'm not going to read through the comments because I was not the best open source citizen. But, I'll let you open this up and read through it if you want to. But anyway, I'm putting this in whitespace only mode because the patch is a lot harder to see without that. But basically, I adjusted uWSGI's behavior adjustment to only happen in an interactive state due to reworking standard IO file descriptors and stuff. But anyway, so that's a little bit off topic, but I did sort of understand after I figured this out, like, aha, oh right, this is because of something that I happen to know very specifically before from patching uWSGI. But anyway, so I added some like things when thread states were initialized and when thread states were swapped to try and understand this problem a little bit better, and then built my copy of CPython and built my copy of uWSGI and ran the same sort of tests with my test suite thing as well. And I got some really interesting output that I didn't quite understand. I made sure to prefix all of my log lines with the process ID so that it was easier to understand where things were coming from or what was going on. In this case, 18901 is the original process, which forks off the two children, or in this case, one child. One child? Yeah, one child. I ended up finding that I didn't need two workers. I could just have one. I saw this weird line here. Swap from thread state a particular pointer to thread state a particular pointer. You'll notice that these two are exactly the same pointer. So I thought something suspicious was here, but I didn't really get too far here. I guess I should take a step back and talk about thread states a little bit. And I'll be the first to say I don't completely understand thread states. They are a part of CPython's internals for how it manages how the interpreter is running on a particular thread, and GIL state and interpreter state and globals of the interpreter. Things that I don't completely understand, but my intuition of it is you have a thread state for what's currently being running. And if you context switch to something else, you need to swap out that thread state so that something else can run. But it struck me a little bit odd that it was swapping from its thread state to its own thread state. But I didn't really get too far on this particular approach and like trying to figure out what was going on here. But I started to get little inklings of like how things were working and how stuff was fitting together here. But this was mostly a dead end. So then I decided to take a step back, and if you recall from here, this issue here, I had identified 3 different things that needed to happen in order for this to be reproduced versus not reproduced. We had sort of gone down the route and figured out what changed in 3.12. We didn't really know why it happened, but we understood what happened here. But I hadn't pursued the difference between uWSGI and PyuWSGI at all. And so that was my next attack to figure out this bug and try and figure out what was happening here, was to figure out the difference between PyuWSGI and uWSGI. Now, a little bit of background here as to why uWSGI and PyuWSGI are different. Actually, it's going to kill this. Okay, that one, it didn't get to the deadlock, so it's killable there. A little bit of background, and I've gave this background in the previous video about the difference between uWSGI and PyuWSGI. uWSGI ships as a standalone binary that you run directly, and that binary brings up the Python interpreter and then uses that to fork off its children and deal with running a web app there. And so it is responsible for starting up the interpreter and then managing all of that state and handing it off to the child processes, etc. PyuWSGI, on the other hand, is a Python module, and it's done this way so it's easier to distribute and build a wheel, and doesn't have to hard link the libpython shared object, so it's portable. But it's a Python module. So when PyuWSGI runs, the interpreter state is already set up, and then it's handed off to uWSGI or PyuWSGI, and it's supposed to sort of inherit that and then deal with all the thread state stuff, and then continue as normal as uWSGI would. And it has to do a little bit of special work in order to do that handoff. And let me show you some parts of that, and then we will do a little bit of debugging to show kind of the difference there. So in order to see that, we need to go into, where are we? We need to go to a copy of uWSGI, which is submoduled into PyuWSGI. And if we get grep for is initialized, let's do this. This is where the, and I'm skipping ahead a little bit. This is where I found out how this difference happens and how uWSGI manages an already initialized is init. Yeah, how uWSGI manages an already initialized Python environment. And so this particular block of code only gets run in PyuWSGI mode because we already have a Python virtual machine interpreter, VM interpreter. You can kind of use the same words for those. And so we don't have to do any sort of initialization and management of Python itself. Now there's also a second part to this, which is the PyuWSGI plugin itself. Oops, open that. PyuWSGI.c, and this is the actual module part of PyuWSGI and how it gets run. The module has 3 functions, 3 methods somewhere. Method. Anyway, there's 3 methods. There's setup and run and something. But the important part, yeah, here it is. Here's the 3 methods. So there's run, init, and setup. You don't have to worry too much about those. But the important one is we're using run, and so we don't super care so much about those other ones, but we have to look at them to understand how the thread state management happens. Because when we're running PyuWSGI, the interpreter already exists, it already has its thread state, and then we somehow have to hand off to uWSGI and have it create its own thread state and manage those itself. And so the way that's done, or the way that it was done, and has very suspicious comment next to it, and spoilers, the bug is in these lines here. The way it does that is it retrieves the current thread state, then sets up uWSGI, and then uses pythreadstateswap to send the original thread state back. So basically, like, this is a Python method, you would call it, it does uWSGI stuff over here, and then it returns back to the original interpreter, and then continues on with execution. And turns out, spoilers, in this handoff here, some undefined behavior occurs. But we'll get to the bottom of that soon. But that's kind of where PyuWSGI and uWSGI differ. And I wanted to also debug and figure out like what actual thing was happening different between the two that was resulting in this behavior. And so we kind of knew from before. You go back a little bit to this backtrace here. Take Gil. That PyEval restore thread was deadlocking in the children. So I thought to myself, okay, we can look at the state of the thread state at PyEval restore thread in both uWSGI and PyuWSGI and figure out like, okay, it deadlocked in PyuWSGI, why didn't it deadlock in uWSGI? And if we look at uWSGI, there's a particular place where this this PyEval restore thread happens, and that's in this file. Do grep-n, no, grep-n. It's on line 12. We'll actually use this later to set a breakpoint here so that we can debug some. But now let's do that actually. So we wanted to figure out where this PyEval restore thread happens and what the current thread status is as that occurs. And we're going to compare uWSGI versus PyuWSGI here. Now, this is actually really tricky to do because we have to spawn a process and then debug its children. And unfortunately on the internet, I couldn't find any good answers to how you're supposed to do this with GDB. Almost all the resources that I found were basically like, yeah, just put a sleep in uWSGI and then you'll be able, or put a sleep in your child process and you'll be able to figure out from there what's going on. And so we're going to do that for both uWSGI and PyuWSGI. And did I already put the patch here? No. There's a patch here to enable debug mode just so that we get better symbol debugging when we step through in GDB, but that's not super important here. We need to find uWSGI fork. This is where the new process gets forked from the parent. I happen to know it's in this file. And the way fork works, I know we're like super advanced stuff here now. The way fork works is if the PID if the return value from fork is 0, that means you're in the child process. If the PID value is positive, that means you're in the parent process, or you know, non-zero. I guess it has to be positive because if it's -1, then fork failed. And that PID will be the PID of the child. So we're going to put a sleep in the child process here, and it'd be a little cheeky and put sleep 20. When I actually debug this, I use sleep 30, and I hope I can catch the race fast enough to figure this out. So let's use our VM uWSGI install. Oops. And we need to reinstall it. So let's uninstall uWSGI, and then we'll install uWSGI. And we basically want to look at what the thread state is after the fork occurs. And so we're going to adjust our little shell script to use the uWSGI virtual env. Oops, that should be $env. Yeah. And if we run this, it should start parent process and the child process. We need to quickly find it. Grab uWSGI, and we need to attach to this one sudo gdb -p. Oh god, 20 seconds. Okay, bad password. Okay, good, we caught it. Okay, so we're in clock nano sleep. We're in that sleep column that we added to this, and so I want to figure out when it does this pyeval restore thread. What is the thread state at that point? So I'm going to put a breakpoint at the line. Remember, we found line 12 before, and so that'll happen. You know, the execution will go back to GDB, and I'll be able to poke around when we get there. So I'm going to do C to continue, and it actually ran directly to this because the sleep had expired. And we're going to try and call pyeval restore thread. Now I happen to know that the global thread state in Python, well, global, it's a thread local. The thread local global thread state in Python 3.12 is stored in this private variable pytss tstate. And if we look at this in uWSGI, the first time it forks, we get null, we get 0. Cool, that's fine. So note that in uWSGI we get null the first time. We can do continue now. And so now we've spawned this. We need to run enough requests to respawn it. Do curl again. Oops. Where are we here now? Okay, anyway, we needed to continue a bunch of times. But now we spawned a new process, and actually we can grab the PID here so I can just attach to it directly. Sudo gdb-p this. We got to catch it before it. Okay, we caught it at the sleep. Cool. We need to set that same breakpoint again. And PID. And basically I want to see the second time it forks what the thread state was as it tries to switch to it. And we can continue. And if we look at that pytss tstate, it's null again. Okay, cool. So in uWSGI mode, we know that the first time it forks, it comes from a null thread state, and the second time it forks, it comes from a null thread state. That's consistent. That's kind of what we expect it to always be the same. But if we look at PyuWSGI now, so let's put this. We kill it? Okay, cool. So if we look at PyuWSGI now, WSGI wheels, uWSGI. What is that for? Yeah, okay, so if we apply the same sleep here, git apply, and go back here, and we use our normal virtual env now, since that's where I put the uWSGI install. We have been pip uninstall pyuWSGI. And yeah, there's some weird output, and that's just from my debug messages in CPython. And if we do bin pip install pyuWSGI wheels uWSGI, this will get us our pyuWSGI version with that special sleep in it. And now let's run that same set of debugging again. Okay, we spawned this sudo gdb-p this. We're at our sleep. Cool. Add the same breakpoint again. So this is the first fork. And if we let it continue along, it takes a while because there's 20 seconds there, and I guess I was real quick this time. Okay, and if we pytss tstate, all right, it's null. Okay, that's the same as uWSGI. Great, that's good. We know this is a working state. Quit this and let it continue along now until we restart it. Okay, we've respawned. We got our new PID here in sudo gdb-p this. So this is the second reload now. We're at our sleep, and that same breakpoint again, and continue along. And we're quicker and quicker this time, so we have to wait a little bit longer until it gets to the next part. Great point to take some water there. And now if we look at PyTSS state, it should be null since that's what we saw in uWSGI, but in PyuWSGI, it's a live thread state. And in particular, it is this same thread state here, where we saw this weird swap from T state to this 2744 value. And actually, I didn't know this at the time while debugging it, but this log line was a bit of a smoking gun. It's telling me here that we're swapping from thread state null to thread state this number. And that's actually this same thread state that we see here. Okay, so we've kind of figured out a difference between uWSGI and PyuWSGI. And so at this point, I was scratching my head a lot. Like I kind of understood another what, but another not why. Like we have two whats. We know some behavior changed in CPython, and this thread state is different between uWSGI and PyuWSGI, but I don't know why those things are causing things. So at this point, I just poked around a bit and read the code, scratched my head a bunch, and did a bunch of debugging that we're going to skip over here because it was mostly fruitless, and a lot of it was just sort of trying stuff. Until I found a little bit of interesting aha moment here. And that is, if we look at the uWSGI code for PyuWSGI, uWSGI plugins PyuWSGI PyuWSGI.c, and we look at this swap call here. The thing that I was noticing here that's really interesting is when this swap and when the fork occurs. And so what I ended up doing is putting basically some prints before and after this uWSGI setup. I'm not going to do it here since it's going to take a while to rebuild it and get it in exactly the right spot. But what I noticed is this function call here was the one that was actually calling fork. And so at this point, the child processes would spin up inside this call here. Eventually this call would return, and then the child processes would call this PyThreadState swap, restoring a thread state and then continuing onwards, restoring back to the original interpreter. And then later on, after this call happens here, PyuWSGI run would happen, and all of the execution would be turned over to uWSGI. But we're in a bit of a weird state there. We've turned it over to uWSGI, and we've restored that original interpreter back, which uWSGI doesn't expect at all. And in fact, the first fork here, when it happens inside uWSGI setup, uWSGI has trashed this original thread state, and so it has set the thread state to null. This is why the first fork looks fine. It has a null thread state, because during setup it's trashed and then forked. But then we restore the bad thread state and continue onwards from there. And so my fix was actually to remove all of this actually do the thing stuff, since all of this thread state swapping and giving state back to the original interpreter is problematic, and moving this directly before any of these uWSGI runs. So in this newer version here, and this ended up being the patch that I ended up fixing it with, this new version here trashes the original thread state and then never gives execution back to the original interpreter. Yeah, never here. That's because uWSGI run never returns. And so in this case, we don't do any weird thread state swapping, and the behavior change in CPython no longer happens. We don't even deal with PyThreadState swap anymore because it's not in the code that gets called now. And so this ended up fixing it. And that was sort of my aha moment, was knowing, oh wait, it's forking during setup and not during run. If it had forked during run, then none of this weird behavior would happen at all. But I wasn't satisfied here. I wasn't satisfied not really completely understanding why it worked fine in 3.11, but didn't work fine in 3.12. I sort of had all the pieces to the puzzle here. Like I knew where the fork was happening. I knew why it was different between PyuWSGI and uWSGI, and now it's the same because there's no longer any return to the original module. But I didn't know why the CPython change was causing this behavior change at all. And I could have just stopped here and been like, yep, fixed the bug, moved on with my day. But, part of me would have never, completely slept soundly knowing that there's some little bit of knowledge about this fun bug that I never figured out. So I decided to try and figure out what's different between CPython 3.11 and CPython 3.12. And I have another directory for that. Basically what I've set up here is a build of 3.11, a build of 3.12, a source directory of PyuWSGI for 3.11, and a source directory of 3.12. The reason that I separated these out is the uWSGI build system is funky, and installing it has some side effect that pollutes the working directory, blah, blah, blah. There's some mess, and so separating these out made it easier to do. And then 2 virtual envs where each of these are installed inside of each other, and then a shell script. And I did the same sleep 30 hack again. So if we look inside uWSGI wheels 3.11, uWSGI diff core, we see the same sleep 30. Well, it's sleep 30 in this case, not sleep 20. And we did the same thing at 3.12. So basically I could do the same debugging that we did before and try and figure out what changed between 3.11 and 3.12 and why was it now deadlocking where it seemed to just do fine before. All right, let's run these two. So VM 3.11. Okay, so let's start with 3.11 first to show what's going on. Actually, let's show 3.12. And then we'll go back to 3.11 and look at why 3.11 was broken there. So if we run this, and we need to wait for it to start up. Actually, I think I can make it go faster. I find this PID and then sudo gdb-p this. Okay, we're in sleep, so I should be able to continue past the sleep. Oh wait, no, that won't help. Anyway, we'll just stall for time here then. Yeah, so this is running here. Let's curl so that it does a reload, because the bug only happens after the first reload. We got a reload here, so now we can attach to this worker. Copy, process exited, cool, great. Sudo gdb-p this. We are in sleep. We can set the same breakpoint that we did before to get that thread state swap and continue. And when we continue, I wanted to figure out why it was deadlocking. My hunch was that it's deadlocking because it's already locked, but I wanted to validate that. And so we're right about to do the swap, and I will save you some I had to poke around in the structures of CPython to figure this out, but basically thread state has an interpreter with the ceval loop with the GIL, and then a locked attribute on that to tell whether the GIL is locked or not at that point. And you'll notice in 3.12 that the GIL is locked when we're about to call pyeval restore thread on the current thread state. So the current thread is holding the GIL, and the current thread state is pytss tstate. Tstate. The current thread state is this one, and the one we're about to switch to happens to be exactly the same one. But anyway, in 3.12 it's locked. So that told me one thing. And in 3.11, if we run the same thing, so back out of this, pkill fg, we got to run the same thing, but in 3.11 now. So again, we got to wait for it to start up, and then we have to wait for it to reload. So that's going to be time to take another sip of water while it does this, because we're waiting on that sleep, because the first fork is fine. It's only the second fork where things go bad or don't go bad, depending on whether it's 3.11 or 3.12. So we gotta wait past the first one. Yeah, okay. So we waited past the first one. Now it's reloaded, so it's going to run the second one here. So sudo gdb-p this, and we're in sleep again. We gotta again set that same breakpoint. Man, this one line was very, very useful in debugging all of this, like figuring out where the thread state swap was happening and then looking at all the stuff that's going on there. Very, very helpful. But anyway, we'll set the same breakpoint. We'll continue. And the structures for thread state actually changed a lot between 3.11 and 3.12. A lot of this was work that went into making subinterpreters possible. And actually, this changed a whole lot between 3.12 and 3.13 as well. In 3.13 to make free-threaded builds work really well, or possible. And so all of these structures, again, they're private, and their internals change a lot between the two. But anyway, I'll save you the looking at all of the structs again. This is the attribute in the thread state in 3.11 that tells whether the thread state is locked or not. And you'll notice here we have our difference. So in 3.12 it was locked, in 3.11 it was not. And we actually know why that is. We know that that changed because of the behavior change inside this patch here. Because in 3.11, this acquire lock doesn't happen when we thread state swap, but in 3.12 it does. And so we kind of have connected all of the dots here into like, okay, we found the behavior change that happened in 3.12. We were able to observe that behavior change and show why relocking here causes it to deadlock in 3.12 because it's relocking the same thread state that we're already switching to. We figured out why that thread state exists at all when in uWSGI it doesn't, and we figured out why this results in a different value here. And so we've kind of pieced together every single little piece of this puzzle and figured out exactly why this behavior change in CPython caused uWSGI to break. Now, the last part of this is, was uWSGI right or was CPython right? And the answer to that is uWSGI had a bug. And this bug had existed since, I think, Python 2.4 is how far back I traced it to. And the problem is uWSGI was running with this particular thread state available while unlocked. And so, basically a thread or data race could have occurred while this was running, but it was highly unlikely because usually when you're running PyuWSGI, you just run PyuWSGI and you don't have threads already present that could result in data races. But there was undefined behavior, and interestingly enough, the restore thread API the restore thread API actually calls out the specific behavior that we were seeing here. Calling this function from a thread, no, not that one. Oh yes. If the lock has already been created, the current thread must not have acquired it, otherwise deadlock ensues, which is exactly what we were observing in the problem state. There was a deadlock occurring inside of PyEval restore thread because the current thread already had the lock held, and the current thread already had the lock held because of the behavior change. So I pieced it all together. I can sleep well now that I've completely understood all of the different parts of this. And I did want to show you the final patch that I ended up making to uWSGI. It hasn't been merged yet, and I've written out notes for basically all the stuff that I talked about in this video. Of course, oh my god, this might be the longest video on my channel. For the hour of stuff that I've been blabbing about, I tried to narrow it down to about 15 bullet points. But the resulting patch, tiny 8-line patch for all of this debugging and almost weeks of time to figure this out, is basically delete the to do ? And move those to uWSGI set. But anyway, that is this debugging saga. I think this is perhaps the most complicated debugging session and the hardest bug that I've had to solve ever. I learned a ton about how the GIL is managed and how thread states are managed. I still don't completely understand them, but I think I know a little bit more now. And I used some really cool techniques, bisection, attaching with strace, with GDB, even some print debugging in some places, and ultimately learned a lot more about how uWSGI works, how CPython works, why PyuWSGI is different, and then the cherry on top is actually finding the bug, finding out why it happened, and then ultimately fixing it. So I hope you enjoyed this journey along this debugging session, and if you have additional questions, leave a comment below or reach out to me on the various platforms. But thank you all for watching, and I will see you in the next one.